Meeting is being live streamed. Okay. Soma.
Can you see that?
Yes,
Yeah.
yes.
Yeah. Hey, Somo.
Yes, yes.
So you are recording now, no?
Yes, yes, yes.
Okay.
Hello.
Hello?
We can start, I think, no? Because some people are on YouTube. They will see that from there.
So do you want me to start now, or are we waiting till the hour?
Professor Krishnendu will.
Yeah. So we still have 2 minutes, so that's why. Yeah. So we start from 5:30 India time. So just maybe 1-2 minutes more, and then we will start. By the way, am I audible properly?
Yes, very much.
Okay.
Actually, it's the same true for me. Can you hear me well?
Yes.
Yeah. So maybe we can start now. Okay. So welcome back, everyone. I see. Maybe I wait for a minute because it's 5:29, and maybe some people may join in a minute or so. But that's okay. I mean, by the time I will finish, everybody will join. Okay. So welcome back to the afternoon session of our workshop today. So today it is a great pleasure to welcome Professor John Parker from Durham University. So John is a very old friend of mine. So it is indeed, I am very happy to see you, John, after a long time. So John will be speaking about elliptic functions and the modular group. And this is the first lecture in his series of 4 talks. And the other talk details will be shared by our organizing coordinator in due course of time. So John, I give it to you for starting the lecture.
Okay, thank you, Krishnendu, and thank you to all of the organizers for this very kind invitation. Of course, I would like it very much if I were in person with you all in India, but at least the technology means that we can talk to each other remotely. I'm not sure whether I can see the chat, so perhaps I'm not sure whether there is a regulation for questions, but I'm quite happy to have questions. So maybe you could probably just interrupt me if we go. Now, one of the themes through this this whole semester is about hypergeometric functions and monodromy. And so the talk that I'm going to give you today is like the very first example, and maybe the simplest and most concrete example of that, which was actually discovered before the whole theory was developed. So this is the work we're talking about today is probably most of it goes back around about 200 years. And actually the subject is one of the triumphs of 19th century mathematics. It's absolutely beautiful mathematics. I will do not have time to do justice to all the beautiful elements of it. For many years, I taught a final year undergraduate course on this topic. So I'm really now condensing 30 lectures down to just one lecture for you. Well, I will try to give you some pointers to where else you can look as we go. So I've got various topics we're going to be going through. I'm going to give you a brief introduction. Then we're going to talk about lattices in the complex plane, elliptic functions, and then we're going to focus particularly on the Weierstrass P function and its differential equation, which is the sort of simplest example of a hypergeometric differential equation. And there is a natural way that the monodromy of that equation involves a modular group and modular functions and forms, and that's where we will finish up. So the main reference for the lecture is the book by Jones and Singerman. That's a very beautiful book, and I think it will be a reference for more than just this talk as we go through. It's very accessible. Probably most of what I'm talking about today you can find in chapters 3 and 6, but there are plenty of other places where there's useful background. So maybe chapters 4 and 5, and I might well be using that in my next talk. And whenever I want to refer to this specifically, I will put references throughout. I will just, my pen doesn't seem to be working, here we go. I will write JS in the slides to indicate a reference from Jones and Singerman. So the point of view that I want to take today is the point of view of complex analysis. And so the course that I have taught, which is based on, is a sort of second course in complex analysis, after people have done the usual like Cauchy theory and Cauchy-Riemann theory of both differentiation and integration. So it's a more advanced talk about power series and so forth. So let's give some very basic definitions. I'm going to let C infinity denote the Riemann sphere. that is the complex plane union the point at infinity, and the topology that we have is the usual topology on C, but neighborhoods of infinity are the exteriors of compact subsets of C. And we're going to view infinity as a perfectly regular point of the Riemann sphere that is in principle no different from any other point. So there's a sort of great democracy happening here among the points of the Riemann sphere. And so if I have a function f defined on an open subset of C, such a function is called meromorphic. If it's either complex analytic, that means it satisfies the Cauchy-Riemann equations, or else it has a pole. And the natural way we write that is that its image lies in the Riemann sphere. So sometimes I will use holomorphic for a function that is complex analytic without poles, and meromorphic for a function that is complex analytic with poles. Then if I have such a meromorphic function, at any point z0 in the domain of definition U, I can express f as a power series. And this power series should be convergent on some neighborhood of this point. And the power series can be written in this form. And there's a special, so I'm starting it not just from 0 or 1, I'm starting it from some natural number d, which may be positive, negative, or 0. And then I'm assuming that the first coefficient is AD, corresponding first coefficient is non-zero. So that tells me where the power series starts. And so obviously if D is negative, this power series is only convergent, is not convergent actually at the point Z0, but only in a punctured neighborhood. So if D is positive, we say that the function f has a 0 of degree d, at, which is the absolute value of d at this point. Similarly, if d is negative, we say f has a pole of degree minus d, which is the absolute value of d at z equals 0. And if d is 0, so the first non-zero coefficient is for the constant function, is a constant term, then we just say this is a regular point of my function. And we're going to be talking quite a bit about zeros, poles, and their degrees. So this is an important definition to keep in mind. Well, just move gear slightly. So I want to talk about a lattice in the complex plane. So if I have W1 and W2 complex numbers, and I'm going to assume that the imaginary part of their ratio W2 over W1 is positive. And then the lattice omega with basis W1, W2 is to be defined to be all linear combinations where the linear combinations are over the integers. So this is a module over the basis W1, W2. But I like to do things in a coordinate-free fashion, and so I do not want my basis, my lattice to depend on the basis. So I want to see what happens if I have two other elements of omega that form a basis. So let's choose W2 prime and W1 prime to be two elements of omega. And so that automatically means that these coefficients A, B, C, and D are integers. And it's a very easy exercise, and you can find this in Jones and Singerman, to say that this new pair W1 prime, W2 prime is a basis if and only if AD minus BC is plus or minus 1. And moreover, we still have this condition on the imaginary parts exactly when we have AD minus BC is equal to 1. So this is your first hint of where the modular group comes in, because I can think of the group SL2Z, which is defined to be all A, B, C, D in SL2R, such that A, B, C, D are in Z, or I could even say this was in M2R, and where AD minus BC is equal to 1. So this is the first guess you're going to have about the modular group coming in later on in the talk. So one consequence of what I've just said is that I do not need to determine a basis in order to talk about a lattice. Now, maybe I ought to also just draw a little picture for you that quite often I'm going to be drawing a parallelogram based at 0, W1, W2, W1 plus W2. And then I can look at, then the points of the lattice are going to be, that I can see here are exactly the vertices. And I can carry on and draw and tessellate the whole of the complex plane with similar parallelograms. And then I could just remove the blue lines. And for example, I could choose a different parallelogram that had a different basis like that. And I should not have written. Okay. So that's given us two ingredients. We've had meromorphic functions and we've had lattices. And these are the two ingredients I need to define an elliptic function. Okay, but so I need to relate the function to the lattice. So this is the notion of a period of a function. So if I have a function defined on an open subset of the complex plane, whose image is the Riemann sphere, we say that a number W in C is a period if and only if for every value of Z, we have f of z plus w is f of z. Now, somehow buried in this is that it should be that f of z plus w, so z plus w should be in u if z is in u, but that's somehow buried, and you could take u to be the whole of the complex plane if you wanted to. Now, notice I've got a function going on to the Riemann sphere, so this statement includes that if f has a pole of degree absolute value of d at z0, then the same thing is true at z0 plus w. And the first observation is that 0 is always a period of any function that you give to me. One of the things that I was often told, and maybe people who've heard me talk before will have heard this before, that every lecture, no matter what subject it is on, should have one fact in it that everybody, no matter how stupid they are, can understand. And this is your fact here, that that 0 is always a period of a function. If I say, if I evaluate the function at z plus 0, that's the same as evaluating it at z. Okay, so we have lattices, we have meromorphic functions, and we have periods. So the definition of an elliptic function is that it is a meromorphic function defined on the whole of the complex plane to the Riemann sphere, for which there exists a lattice omega, so that every w in omega is a period of f. So these periods that we had just slightly above, for every point in the lattice, then I have an equation like that. And of course, we call omega the period lattice, or a period lattice of f. Now, the second observation is that any constant function is elliptic. In fact, for a constant function, any number is a period of that function. Of course, in a couple of slides' time, I'm going to construct more interesting examples. But so far, everything I've said, we don't yet know whether it's vacuous or whether it only applies to the constant functions. We'll find out more in a moment. So if I have an elliptic function, any constant multiple of it is elliptic. And also there's a little calculus that the sum of two elliptic functions, their product and their ratio are all elliptic, provided that in the case of the ratio, the denominator is not identically equal to 0. So this condition here is supposed to apply only to C. So I can merrily and freely multiply, add, and multiply by constants any elliptic function. We'll do that fairly freely later on. So I told you in the abstract that I wanted to think about some geometry. So I want to just think, so geometrically, what you should think of is an elliptic function gives you a complex analytic function from a torus to a sphere. In the same way that a rational function gives you a complex analytic map from a sphere to a sphere. So how does that work? Well, if I have my elliptic function f from C to the Riemann sphere, that's up here. I also have the quotient map that would identify two pairs of points, a pair of points, if their difference lies in the lattice. So this is the quotient map here. So this means that Z is related to Z plus W for all Z in C and for all W in omega. And then this is the space of equivalence classes of that relation. Then, and somehow I can move downwards to my, or rather I can take my quotient thing, which is a torus. That's quite easy to see. You just identify opposite sides of this parallelogram. So maybe you have opposite sides being identified like this. So if I have a point on this torus, I can lift it upstairs, and then I have an elliptic function that's will be well defined on this pre-image, and that moves across the Riemann sphere. So I can push this whole diagram down and define something down here so that the diagram commutes. So this becomes a complex analytic map from a torus to a sphere. And this is something we're going to keep in mind in the back of our minds throughout. And I'm going to come back and give you various other different ways to understand what that means. Okay. So I think this is what I'm about was just said in fact, but so let f be an elliptic function with period lattice omega. This is a statement that's going to happen again and again. So just remember what that means. It means that omega is a lattice. Every W in omega is a period of f, and f is also meromorphic. So what I just said on the previous slide, 2 points are congruent mod omega whenever their difference lies in omega, which defines an equivalence relation. The function has only finitely many poles mod omega. That's again, you can find that in Jones and Singerman. I can't remember exactly where. And we define the order of the elliptic function to be the sum of the degrees of those poles. So if I come back over here, then that means that somewhere there's a whole bunch of points whose image is the point infinity, which is traditionally the North Pole and the Riemann sphere. And then all I do is what I'm going to do here is I'm going to count the number of pre-images of infinity on this torus. Okay, so any elliptic function with order n equals 0 is constant. And so there's a proof in Jones and Singerman. This is a beautiful application of Liouville's theorem. It's a very, very simple proof, but it's a very powerful result, and it's very beautiful. And what that would mean is that if I were to take a function from the torus which does not to the sphere, that misses out this point at infinity, then it's forced to be a constant function if it's a complex analytic function. There are no elliptic functions of order n equals 1. Well, let's just think about what would happen here if that was the case. Then this would be a map from the torus to the sphere, where this point at infinity would have only one pre-image. A little bit later, we're going to see that if that point has one pre-image, then so would every other point. And because we know the sphere is not homeomorphic to a torus, that's impossible. But in fact, the way you prove that using complex analysis is completely different. You use the residue theorem by integrating around this period parallelogram, and it's beautiful. But again, I don't have time to talk about this level of beauty. But now, if I have n bigger than or equal to 3, and that's important, there's 3, then there's a function that I can define like this, where for every w in omega, I can define that elliptic function that's of order n. And in fact, fn has a pole of order n at each w in omega and no other poles. So, and also I wrote that series, infinite series. I haven't told you about the convergence. That, in fact, this is converging in the nicest possible way. It's converging absolutely, and it's also converging uniformly on compact subsets of C. This is the nicest possible sort of convergence we could have. So we've treated the example of n equals 0, n equals 1, and n bigger than or equal to 3. That just leaves n equals 2. So that's what we need to do next. And so this is the Weierstrass P function. So this symbol P, Weierstrass had some strange sort of handwriting, I believe, and so he wrote his P in this particular script. And so the makers of LaTeX have given us a special symbol for this special Weierstrass P function. So when I've been teaching my students this, I've given them a handwriting class of how to write this P and told them to practice. So perhaps this is a little bit of homework you can do if you wish. So we want to define this function P. So on the previous slide, we talked about this sum over all points in the lattice of 1 over z minus w to the n. Well, so if we were to try to do this with order n equals 2, that's our first guess. Unfortunately, that does not converge. So we have a problem. Fortunately, Weierstrass comes to our rescue, and he says that if we actually subtract off 1 over w squared, then and I have a sum like this, then I converge. But of course, if w is 0, that also gives me a problem. So I take out the term corresponding to z equals 0, which would be 1 over z minus 0 squared, and then I take my sum over all remaining points in the lattice. And the meaning for these brackets here is you should think of this is a sum where the term is exactly the things inside the parentheses. The two terms themselves individually do not converge, but their difference does converge. And that's very important. It's an easy mistake to make to sort of separate things out. Okay, so this is an elliptic function of order n equals 2, has period lattice omega. It has a pole of order 2 at all w in omega and no other poles. And this series converges absolutely, which means that I can freely rearrange the terms in the sum. I mean, technically speaking, I should have chosen an ordering on my lattice and said it was in that particular order and only later written it like this. But because it's absolute convergence, it doesn't matter which order I take. It also converges uniformly on compact subsets of C. And this means that I'm allowed to differentiate term by term. And so if I do that, it's not too hard to see differentiating the first term, the 1 over z squared, I get minus 2 over z cubed. If I differentiate the term inside these parentheses, the 1 over w squared goes away, and I get minus 2 over z minus w cubed. And that just is minus 2 sum w in omega 1 over z minus w cubed. So that's just this f3 function we saw before. Okay, so let's just think about a bit more geometrically about elliptic functions of order 2. And here's a way of trying to construct a map from the torus to a sphere. So imagine you take a torus, and let's really think physically. Let's imagine this is a donut, and I want to barbecue my donut. Maybe, I don't know, do you barbecue in India? But if I do, I want to put a skewer through the middle of this donut like this. Let me use my pencil to do that. and so that I would be able to rotate it around this axis. That's what this first picture is supposed to mean. And so that means that every point on the torus, with the exception of the point where my skewer goes through, there are 2 points that correspond to this if I do a pi rotation. So let's just choose one of them. And so I get something that looks like a cylinder. And then I would have to, with the boundary circles, I would just collapse them so the opposite points get identified. What do I get left with? I get left with something that looks like a sphere, but with 4 special points, which are remember where this skewer went through my donut. And so this is a nice smooth map, apart from at these 4 points. And at those 4 points, I'm going to get a cone singularity of cone angle pi. And let me just make a slight diversion at this point. There is a beautiful theory about monodromy by Thurston, which is all about taking cone points on a sphere and looking at the moduli space for them. And that's something that I can't cover, I don't have time to cover in this lecture, but it's something that you should, if you're interested, you should read, and I would recommend this. So there's a paper by Thurston, and it's, I can't remember the exact title of the paper, but it appeared in the Epstein birthday shrift, which is Geometry and Topology Monographs, Volume 1, in 1989, 1999, I think. I don't know. 1990. I don't know, some year, 1989, maybe. No. Anyway, no, 1999. Sorry, that was the original manuscript. Okay, I'll remove the year to save confusion. Anyway, so that was an aside. So, and you can find this theorem without the geometrical interpretation written in Jones and Singerman again. Right. So that one of the main interesting properties of P is it satisfies a differential equation. And so what I want to do is I want to derive this differential equation for you. And so we're going to go through this step by step. So this is perhaps more detailed than I have been previously, but this differential equation is really important, and how you construct it, it's a completely beautiful construction, and I think it deserves a little bit of time for us to take a little bit of time on this. Okay. So I'm going to define a series. These are called the Eisenstein series. GK, where k is greater than or equal to 3, where I sum over the whole of the lattice apart from the origin of 1 over w to the k. Now, the reason I have to take k greater than or equal to 3 is that in order to make it converge. So this, I should say, converges for k bigger than or equal to 3. In fact, if I took real powers, it would converge for k strictly bigger than 2. Notice that if I have k being odd, then in my lattice, I always have, I can always take w and minus w in my lattice. If w is in the lattice, then minus w automatically is. And so when I take those two terms, those two would cancel out. And every point in the lattice, apart from the origin, has a unique friend who is minus itself and different from itself. And so that means that when k is odd, all of these Eisenstein series give me 0. So in fact, the first interesting one is G4. Let me take my series for P of Z, and let's start to think about what happens on a disk around the origin. And I want to make a power series, and I want this power series to converge on this disk. In fact, The radius of the disk is going to be the absolute value of the smallest non-zero element of the lattice, but it doesn't really matter. This R exists. That's all that we care about. So now what I want to do is I want to expand this term here as a power series. So one of the ways to do that is to use the geometric series. So you know that 1 over Z minus W is going to be 1 minus Z over W. Oh, sorry, it's going to be W. I should have a 1 over W. It's 1 over W squared plus Z squared over W cubed plus and so forth. And then if I differentiate this, this converges uniformly on compact sets. So I can differentiate term by term, and I can find that 1 over Z minus W squared is going to be what? It's 1 over W squared plus whatever it is. It's in this power series here. K plus 1 over, so I'm going to have a 2Z over W cubed and so forth. So that's all I've done here is I've just expanded this term out, and notice that the first term 1 over W cancels. So this is just simply inside each of these terms, I've expanded as a power series. Now I use the fact that I have absolute convergence, and so I'm allowed to reorder terms. And so what I'm going to do is I'm going to switch the order of the summation here. And once I've switched the order of the summation, then I see that I keep this Z to the K out there, and I get this GK plus 2 from this Eisenstein series that we had up above. Great. And then I notice that I have the Eisenstein series, but half of them are 0. And so what I'm going to do is I'm going to write K is 2n for when K is even, and then this gives me a power series down below. And this power series converges on some disk. I should say a punctured disk. Obviously, it doesn't converge at the origin because of the 1 over Z squared term out of the front, but the rest of it converges at the origin. I hope that's clear. One of the disadvantages of giving these talks like this is I have a lot of blank screens and I have no feedback. So I'm hoping that if this is not clear, somebody will yell out. So let's just write out that series now for the first few terms of it. So I have 1 over Z squared. Then the first term for n equals 1, I'm going to get 3g4z squared plus 5g6z squared for n equals 2, and so forth. Now I have uniform convergence on compact sets, so I'm allowed to differentiate term by term. And I get this series here. And where am I going? Because suddenly this all may seem a little bit odd. Where am I going? What I want to do is I want to use these power series to cook up some combination of P and P dashed, the derivative of P, so that it has no terms in the principal part. So there are no terms with a 1 over Z or higher order terms. Everything else is just a regular power series in Z around the origin. And what will that do for me? That will mean that this particular combination of these functions does not have a pole at the origin. Because these were elliptic functions whose only poles were at points of the lattice, then it cannot have a pole anywhere else. And the power of this theory that we've developed, and the beautiful aspects of it, that means the function has to be constant, and I suddenly get some relation between P and P dashed, and that will be the differential equation. Excuse me. So let's do that. I touched something and I have now lost where I was. Here we go. the danger of trying to do stuff on an iPad. So the first thing I'm going to do is I'm going to square p dashed of z. So again, I'm going to use absolute convergence, so I can just gather terms of the highest order, and then I'm going to have some sort of remainder term. I'm choosing to keep to do my remainder term for everything with a positive power of z. So I'm going to have z squared, and this function here is going to be holomorphic, means complex analytic at z equals 0. So let's see what happens. Well, if I square this term, I'm going to get a 4 over z to the 6th. Then I'm going to get a cross term between here and here. That's going to give me minus 24 g4 over z squared. Then for my constant term, I'm going to get a cross term over here. So I'm going to get minus 80 g6. That's my only constant term. And then everything else that I get, I'm going to get probably a 36 g4z squared, and then there's going to be some other cross term involving the other terms. But I don't care. I just put it in this remainder term. Well, I see a 4 over z to the 6. So that gives me a little bit of a clue that if I want to eliminate this using the p, I have to do something where I have to probably cube my p and multiply by 4. So let's look at what happens with 4p cubed. And I do a similar thing, and I get 4 over z to the 6th, and I get these terms here, and then I throw away all the positive powers in this remainder term, where again, phi 2 is holomorphic at z equals 0. Well, that's great. That means that these two terms have cancelled out, and I get just some constant times z squared, and then I'm done. So the constant, it turns out, is 60 g4. And so I write 64 g4 pz, and I get another thing there. And so what I can do is I can take my first term and subtract the other two terms. I get a constant term. I'm going to subtract that. And then this is all going to equal something like z squared times whatever it's going to be, phi 1 minus phi 2 minus phi 3, and that's going to be it. But it's some holomorphic function, so I have a power series starting with, at the very least, z squared. It may be that it's a lower order term, but I don't really care. Great. And so that means that from the last slide, this function here has a power series about z equals 0, starting with at least z squared. It's an elliptic function with period lattice omega, only possible poles at points of omega. Now, since it doesn't have a pole at z equals 0, that's why that's the first of those bullet points. It can't have a pole at any other lattice point. Therefore, it has an elliptic function with no poles, and so that means it has order n equals 0. And so by the theorem we had earlier on, that means it's a constant. You see, all these things I was doing earlier, they're like things when I'm cooking, I'm making little pieces and putting them to one side, and now I'm going to assemble the whole dish. I'm going to bring them all in together. So since the power series at z equals 0 starts with at least z squared, it must take the value 0 at z equals 0. And so that means the constant 0. Right, so suddenly this is just a beautiful slide. I'm just gathering together all these other little pieces that we've had. And so this means we have this differential equation where I don't like this 60 and 140, so I'm going to rewrite those as G2 and G4. And that is the differential equation that's satisfied by P. And that's very, very important. So what I want to do before we move on is I just want to give you some consequences of how this differential equation is useful in other areas of maths. So first, in algebraic geometry, you might have heard of elliptic curves. They're curves, they're solutions to polynomial equations of the form where you have a square on one side and a cubic on the other side. And so this is an example of an elliptic curve. And if I were to substitute x was equal to p, y was equal to p dashed, then I would have excuse me, then this would give me something that would satisfy this this algebraic equation. And so the solutions are a torus, because we've already seen that the elliptic function corresponds to a torus. And in fact, that's conformally the same as the C mod omega. So this relates very, very concretely a particular torus with a particular lattice, W1 and W2, with a particular algebraic curve. And sort of maybe to make a slight side remark, going between algebraic curves and Riemann surfaces is in general very difficult, because if you hand me, in theory it's easy because there's a one-to-one correspondence, but actually finding what that is very tricky. And here, this is the recipe. You would go between the two of them. The second application is in elliptic integrals. So if you find for me somewhere in nature an elliptic function, an integral which is of the form 1 over the square root of this particular cubic equation, I may want to solve it. Now, you're all used to the fact that if I were to take 1 over square root of 1 minus z squared dz, then I would use the substitution z is sine of u, and then I would get down to that then I would have integral du, which would be arc sine, which I could write sine inverse of z plus c. So in exactly the same way, I can make the same substitution of p of u, and I can evaluate this integral via the inverse function to an elliptic function, to this particular elliptic function in this particular case. Later, we'll see that we can do this in more generality, but at the moment, it's just this particular value of G2 and G3, which I can do this. And in fact, the reason why these are called elliptic functions is if you were to try to calculate the arc length of an ellipse, and then you do some suitable changes of variables, you will get down to an integral that is exactly of this form. That's why they're called elliptic functions. I want to give you another version of the differential equation, which effectively comes from factorizing this cubic equation. A fairly simple argument using absolute convergence shows that P is an odd function. So let's just run through how this would work. So let's evaluate P dash, sorry, it's an odd function. So let's look at P dashed. We know that it has this form, but I'm substituting in minus z instead of z. Well, what I can do is I can take this minus sign out, and I can put a -1 on the top and turn that into a plus. And that's great. That's almost the right form for the elliptic function, except to have a plus w instead of a minus w. But I know that if w is in the lattice, then so is minus w, and so that's fine. We have to take special care of the origin, but actually that's all right. And so I discover by rearranging terms that I can rewrite it like this. And that's just minus p dashed of z. So this means that, so in fact, yeah, so p dash, what? Lost it, there you go. P dashed is odd. Now, suppose that we have any point in the lattice, but which half of it is not in the lattice. So remember, that could be something called MW2 plus NW1. All I'm saying is that both M and N cannot be even. This means then that z is w over 2 is not a pole of p dashed of z. So if I evaluate p dashed at this point, I could just rewrite this. This is just a half is 1 minus a half in a fancy way. And then this is just simplifying this to give you minus w. And then I'm using the odd function here. And so the upshot is that p dashed of w over 2 is minus p dashed of w over 2. And so that means that p dashed of w over 2 is 0. Up to equivalence mod omega, that applies to exactly 3 particular points in C, namely w1 over 2, w2 over 2, and w1 plus w2 over 2. Remember, w1, w2 is supposed to be a basis for omega. So now let's evaluate. So that was what happened for p dashed at those points. Now let's evaluate p at those 3 values. And they're going to be, I'm going to call those E1, E2, and E3. Now, it's a little bit, it's not so difficult to see that if I were to take the right-hand side of the left-hand side of the differential equation, that should vanish when z is equal to one of those 3 values, w1 over 2, w2 over 2, or w1 plus w2 over 2. And that means the right-hand side must vanish as well. And that would mean that we have a factor of p of z minus ei inside this cubic. The cubic then is a product of 3 linear terms. And you need to use a little bit more but facts that you can, easy facts you can derive about elliptic functions, and Jones and Singerman do that sort of show you that the differential equation is precisely that, that cubic equation. So I've written a slightly different way by factorizing the cubic. And moreover, the roots of this cubic are distinct. And that's a really, really important thing. So in particular, if I took the cubics in my algebraic geometry, algebraic curves, or in my my elliptic integral, they must have distinct roots. We're going to come back to this later when we're talking about hypergeometric functions and monodromy. And in that case, it's normal to then apply some sort of rational map, or in fact, in this case, it would just be a similarity, so that E3 is 0 and E1 and E2 is equal to 1. But we're going to talk about that later on. That's just an advance warning. So I want to talk to you a little bit about, I'll give you a more geometric flavor of what's happening. And I want to do this using somehow the old-fashioned view of Riemann surfaces as branched covers of the Riemann sphere. And to just motivate this, I want to think about the square root function. So how do you define the square root function on C, or in fact on the Riemann sphere? I'm going to think about taking, this is my C, in fact it's going to be my C infinity, and then what happens is above each point here, I'm going to there's going to be an upwards arrow here, which is evaluating the square root. And so what happens at most points is that I have 2 square roots. I have a square root on the, which is sort of, I think I was being on the upper sheet, and a dotted square root there on the lower sheet. And if I were to just move my point around, what would happen? Well, if I just move in a little bit, I still stay the same square root. This is a continuous function. But if I analytically continue all the way around the origin, so this blue point there is supposed to be the origin. If I analytically continue around there, then I sort of come back on the lower sheet. I move from the positive square root to the negative square root. Of course, for a complex number, positive and negative don't really mean anything, but that's just a way we talk about it. So often what we usually do is we cut the plane along the negative axis. So what I'm doing here is that let's do that, but remember that we need to if I'm doing on this branch, when I come around and I glue to here, then I need to emerge on this side. So what I've done is I've cut the negative real axis, and then I've sort of opened it out, maybe with a pair of pliers or something, so I can see both sides of it, and I've colored them according to how they're glued. And if I were to glue everything back together, I get the Riemann sphere. And so what I'm doing is the square root function is sort of coming along here. Right, so it's a double cover of the plane, but it's well defined everywhere and it's smooth everywhere. Because around the branch point, I have a little neighborhood that has to wind twice around. So let's do the same thing with this function here, which is now the square root of this cubic polynomial that we had before. And so here I'm going to think about these three values, E1, E2, and E3. Okay, so what I do this time, instead of just cutting the negative the negative real axis, I have to, which goes between in the previous case 0 and infinity, which were the two singularities of that map. Infinity only has one square root on the Riemann sphere, namely infinity. 0 only has one square root. Now we're going to do the same here, except I have 4 points, namely infinity and the 3 points E1, E2, and E3. I cut along the line from any old line from E1 to minus infinity, and another line joining E2 and E3. And then I can glue again using the same recipe. Now I have to remember to put a little line so I know which of the red lines to glue to which. And if you stare at this hard enough, you will see that the result that I get is a torus. So, well, again, you have to sort of think about this for yourself. But what I'm doing effectively is I'm taking a sphere and I'm removing two little discs here, taking another sphere and removing two little discs, and then I'm gluing in. You can think of it as this gluing operation, as I could glue in two cylinders, and you see that the result looks like a torus. Or if you wanted to, you could just take a halfway point on here, and you could just deform this sphere so that it filled out all of that. And notice that there are exactly 4 points here. And so if I were to do what I did earlier of take, I want to do it in yellow, let's take my barbecue and skewer through my torus on those 4 points, and then say that I've got the points that differ by pi rotation around would just get me back to the sphere. Then I'm just inverting this whole operation. So there's a beautiful way of going around, of passing from the torus to the sphere and the sphere back to the torus again. So this is effectively the inverse of my elliptic function. Okay, in the last section now, we're going to see what happens when I've just done something. What's happened there? I hit the wrong thing. Sorry about this. I'm back on the right page. Phew. Right. So we thought about a particular given lattice, and I constructed the Weierstrass P function from that particular lattice. But there's nothing sacred about that particular lattice, and I might be able to choose a different one. And now I want to think about what happens as I vary the lattice. In fact, I want to think about functions that arise as I vary the lattice. Okay, and so in particular, I want to think about which particular cubic polynomials will arise in the differential equation, and hence in the algebraic geometry and the elliptic integral when I start to vary the lattice. So remember, I had my lattice was MW1 plus NW2, where M and N are integers. And I'm going to define their ratio. That's a bad color to use. Define their ratio W2 over W1. And because they're at the imaginary part of W2 over W1, it's the same as the imaginary part of Tor is positive, then this number lives in the upper half plane, which I'm going to denote by a curly U, a script U. I'm trying to use the same notation as Jones and Singerman wherever possible, and they call it a calligraphic U. Now, it's a little bit awkward to vary my lattice with two different variables. And so I could think of this as being in C2 or C2 in some subset where W2 over W1 is positive. But it's not so difficult to see that if I were to scale my lattice, then what happens is I end up scaling my elliptic function by a constant, and I end up with essentially the same thing. So what we're really interested in is lattices up to scaling. And so what I do is I'm now going to scale my lattice. In this case, I'm going to divide throughout by W1. And so this means that I can think of my lattice with a new basis, 1 Tor. And now my lattice just depends on one complex parameter in my upper half plane. And every point in the upper half plane corresponds to a basis of a lattice. But I said earlier, I don't really like having to keep track of which particular basis it is. So let's see what happens when I change basis. Well, before we saw earlier that if I have two other points in my lattice where they must have integer linear combinations, and suppose that we have the ratio is again, the imaginary part is positive. And so that means that we have to have AD minus BC is equal to 1. That's the result we had earlier. And so that means that the map that sends Tor to Tor prime is a Möbius transformation whose determinant is 1. So this actually lives in PSL 2Z. Watch, I've just said that here. So that's the group of all Möbius transformations with integer coefficients whose determinant is equal to 1. And we notice, again, we emphasize this, that moving from a basis 1 Tor to a basis 1 Tor prime, that involves scaling the lattice. So that's just very important. So we can view these functions G2 and G3 now as functions of the lattice. Remember that G 2n is the sum over W in omega 1 over W to the 2n, which is the same as the sum mn in Z2. And I had to also say that this was minus the origin, mn 0, 0, 1 over m W1 plus n W2. And now if I'm thinking about this basis, I can cross out that and put a Tor there. But remember that there's some factor of W1 that I've had to take out. So anyway, what I can do with respect to this basis, I can write G2 as this function, and I can write G3 as, and I missed out a 60 here, and I've missed out a 140 here. Sorry about that typo. And both of these series are going to converge absolutely. In fact, these are both holomorphic functions from U to C. So they're complex analytic without poles. But I've done that again. Sorry. I keep hitting the wrong things. That was where I was before. Here we are. Good. So what happens if I do this change of basis now? Then there was some scaling involved, and it turns out that these functions, this is what I get. And I should notice that in Jones and Singerman, there is a typo at this point because they put the wrong sign in the in this exponent here. So a function that changes according to one of these elements of the modular group, but where you have to pull out a power of C Tor plus D is called a modular form, and the weight of the modular form tells you what power that you need to pull out. And so this means that G2 and G3, these are modular forms of weight 4 and 6. We sort of want to do something that is a little bit like what we did for elliptic functions. We want to have something that changes nicely with respect to the change of basis without having to scale. That's going to be called a modular function, and that's what I want to construct now. And I just see my time is up. I don't have very many slides, so may I beg your indulgence and just have a couple more minutes. So remember, this cubic here had distinct roots, and so, well, up to some constant multiple, its discriminant is this value and is non-zero, and a little bit of calculus with this G2 and G3 shows that this is a modular form of weight 12. So the modular function is defined, called J, is defined like this. It's defined to be G2 cubed over this discriminant function. It's a holomorphic function from the upper half plane to C. And whenever I change variables according to an element of the modular group, then this whole function changes nicely. So and so this really is a very powerful thing. So you could imagine that this is you could think of equivalence on the upper half plane via the modular group, and this is a function defined on the quotient space of this. So in fact, what we have is we have the upper half plane, and we have some tessellation by I'm making a mess of my little drawing here, and where each one of this region is replicated many times, like my parallelogram was before, and I can pass down to the quotient, which it looks like a complex plane with two singular points, and I have a map across to the complex plane, and then I can have the same map here. This would be my function. Right, now there's various beautiful facts about this you can find in Jones and Singerman, that this map that I've just drawn here is 1 to 1. So for every point in C, there is exactly one modular group orbit in the upper half plane for which J solves this. And as a consequence of this, you can always find, if you have a cubic with distinct roots, that means the non-zero discriminant, you can always find a lattice for which there is an elliptic function with that period lattice satisfying that particular differential equation. So the algebraic geometry and the elliptic integral we had earlier, they were for a particular cubic. Now I have this for any cubic with distinct roots. I was going to tell you about the lambda function. The lambda function is something that's going to be related to monodromy, and it satisfies something where we have a subgroup of the modular group. We don't really have time to talk about that, but suffice to say that those three values I had, E1, E2, and E3, if I take E3 to be 0, E2 to be 1, and allow E3 to vary, then I'm going to, I get some beautiful things. So I think Krishnendu has come on the thing, so that's the equivalent of standing up. So I think I'm now 4 minutes over, so I will stop there. Thank you very much.
Yeah. So John, I think if you want, you can continue and finish your rest of the 2 slides. If you
okay, so should I just go? I'll go back to the previous one and just go slightly more slowly through that. Thank you. That's very kind of you. Okay, so let's just come back and do this slightly more slowly then. So so we had 4, remember I keep drawing 4 points on the Riemann sphere. And there's a conformal invariant of that, namely their cross ratio. So let's take the cross ratio of those 4 points of infinity, E1, E2, and E3. And there is various conventions with the cross ratio, but I'm going to take the one given here, which is the one that Jones and Singerman use. And notice that if I take E3 to be 0 and E2 to be 1, then this value, this function lambda, exactly takes the value E1. Okay, so what happens if I change apply an element of the modular group to this lambda function, this cross ratio? Well, these 4 points get permuted around somehow. And therefore this cross ratio also gets permuted around. And there are 6 possibilities depending on the 6 possible permutations that, well, actually there are 24 permutations, but the way cross ratios work, they only ever have 6 possible values. And that depends on the parity of A, B, C, and D. So what I've got here is I've got a little table that tells you, this is an exercise in Jones and Singerman, so this is your free bonus. I'm going to give you the answer to that exercise. So let's look at the first line here. So if A is odd, D is odd, and B and C are both even, so these little symbols O and E are supposed to represent odd and even. Well, for example, the identity map satisfies this. It's not so hard to see that when I change these new values, so EI prime is P of a half WI, where I'm thinking of W3 as being W1 plus W2. That, I noticed another typo, sorry, that should have been an E3. So then this lambda doesn't change because E1 prime goes to E1 goes to E1, or E1 prime is E1, E2 prime is E2, E3 prime is E3, lambda is the same. Now look at what happens if I get B is also odd and D is odd. So for example, I could take the function Tor goes to Tor plus 1, where this would be A is D is equal to B is 1 and C is 0. Well, a little bit of working it out shows that E1 stays the same, but E2 and E3 have swapped. And this means that lambda prime is 1 minus lambda, and so forth. And you see that I get lambda equals lambda prime exactly in this case where I have A and D are both odd and B and C are even. And there's going to be a subgroup of gamma prime, of gamma called gamma 0. That's a congruent subgroup where that's true. So that's what we have over here. So I have lambda of Tor prime is lambda of Tor. That's what I just said. If and only if I'm in the group generated by those 2 transformations. And in fact, that is an infinity triangle group. We're going to talk about triangle groups in a later session and fundamental domains. So this is, maybe to understand this slide, you'll need to go to those talks and come back. And I'm going to make these slides available, so that's also fine. But it will have a fundamental domain, which is made up of two hyperbolic triangles, a hyperbolic quadrilateral that looks like the one I have just down below. And so this map T corresponds to identifying the left-hand side with the right-hand side, and S corresponds with identifying this semicircle with this semicircle. And once I do that, I get a Riemann surface that is, it looks like a samosa, but with infinitely long points. Right. So the differential equation in this case becomes has that form. And the whole idea of monodromy is I want to look at the solution of this differential equation, and I want to allow it to vary until I come back to where I started from. So let's take this. So if I'm fixing the other two, I'm just taking this lambda. I could think of taking lambda on this walk that goes along the green path upstairs. And what happened, that the Tor goes along this green path, sorry, and the lambda then walks on this green path around infinity down below and comes back. And similarly, if I go along this red path, if the Tor goes along the red path, then the lambda varies along the red path and comes back to where I started from. And then, so this is the whole idea of monodromy. So if I were to, I can always go backwards. If I take this differential equation and I allow the solutions to vary along this path, remember lambda is not allowed to equal 0, 1, or infinity. So that's I cannot shrink those paths to 0. There's some non-trivial topology happening. Then that is equivalent to sending this Tor on my lattice, defining my lattice, going along a path from some value, maybe -1 plus IY to +1 plus IY. And that takes it along this thing. And so then there's a group element, and that's going to correspond to this. So the whole idea of monodromy is going to be, I'm going to have a differential equation which has 3 singular values, and I want to look at solutions and how they vary along these topologically non-trivial paths that go around those singular values. And I'm going to end up with triangle groups. And so this infinity triangle group, this dates back to the very early part of the 19th century, but then, or the middle part maybe, but then H.A. Schwarz showed that so you can arrive at any triangle group as a monodromy of a differential equation like this. And I believe that that's what the next talk is by Venki is going to be. At least this is my understanding of what he should be talking about. Maybe he's got some much more interesting things to talk about, but exactly how you can take these differential equations, you find functions that solve them, and you find triangle groups as monodromy groups of those equations. Okay, I'm going to stop now and allow you to ask some questions.
Yeah. So Sasha, you can ask.
John, of course, first of all, thank you very much for a very beautiful exposition. I know the subject, but it was a real pleasure to hear this again. But my question is maybe very naive. The situation is the following: Taurus under consideration. This is a Euclidean Riemann surface. It can be uniformized by Christological group Z plus Z, which acts without fixed point. But we also know that there are 17 Christological groups, except this one. What about another guys, for example, Klein bottle and other things? Could you say something about elliptic functions defined on this orbifolds? Or this 17
okay, so let me, for the moment, put the Klein bottle to one side, but think about the ones that do not have orientation reversing isometries.
Yeah.
So the simplest example would be the crystallographic group, which is of index 2 in a translation group, which would correspond to having a sphere with 4 cone points of order 2. And that's exactly the picture that we had earlier on. And so, in fact, any lattice, you can do that. So perhaps let me, I need to start to draw some pictures now. So let me just move over and open another. Okay, so what I was talking about earlier was we had a torus where I could identify opposite sides, the parallelogram, and as a result, I got a torus. Now let's look at, there's a rectangle, a smaller parallelogram here, where I would identify opposite sides like that. But then I would say I've got some other identifications. So I'm going to identify these sides via a rotation that would fix this midpoint here.
Sure.
Then it's not so difficult to see that if I were to sort of triangulate it like this, what I could do is I could get a tetrahedron where what I've done is I've got the 4 points like this and a path that goes around the edge like that when I identify them together. And so now I can think of this, all of what I was talking about, as being like fixing 3 of those points and allowing the 4th one to move around and to go on paths around on this sphere, so long it's just not allowed to collide with the other ones. And this is the basis of the things by Thurston that I was talking about earlier. Okay, that was my first comment in response to your secondly, that there are perhaps some special tori, namely there's the square torus and the hexagonal torus, and those are going to correspond to very special orbits in the upper half plane, namely the orbits of I and of the cube root of unity. And so those are very special points. And so that's a particular example. And again, you can see in Jones and Singerman how to derive exactly which points of the upper half plane correspond to those. Now, for things with Klein bottle, so again, you're going to be having a double cover is a torus. And so I'm going to have something slightly more complicated down here, which I haven't particularly thought about. Probably I'm going to be doing a reflection, so I'm going to have a surface with boundary. No, I'm perhaps not a reflection. Anyway, I haven't thought of exactly how the Klein bottle would work, but yes, you can do very similar things to that. Does that answer your question, Sasha?
I mean function. What about elliptic function? You start with this P function by Weierstrass, but then you modify it for torus, for this orbifold, for other things. Probably this is just combination of P functions of Weierstrass with some particular coefficients and so on and so on.
It's going to probably be anti-holomorphic, I think. I think it's going to be an anti-holomorphic function. Because is that right? Because you're swapping your W1 and W. Yeah. Not sure. Good question. Maybe we can leave to exercise to all of the students who are learning this material.
Yeah. Well, it's just for funny, but maybe something serious is behind. Thank you very much. I completely agree with you.
If I stop sharing as well, that maybe is going to help as well.
Yeah. So any more questions or comments?
Yeah, hello, John. John,
Yes?
it's not a mathematical question. I would like to know about Millington. What do you know about her?
Millington. Yes, I know. Hi, I know where this question's coming from. I know that Millington was a student in Durham, and she was a PhD student of Oliver Atkin, and she unfortunately died very young. But she has a theorem which is exactly related to this, and you told me in Almora that she was a woman. So thank you for telling me that. And I actually also went out to find out.
So she was much senior to you.
Yeah.
Okay. Do you know anything else about her?
I asked somebody about her, but I don't think I have very much. So there is an obituary of her, I think in the LMS journals. So.
I see. Okay, thank you.
Okay, so
this is a slightly funny story that I was giving a talk in Almora about, and I was referring to this theorem of Millington. All I knew was this was H.M. Millington. And so I made a very politically incorrect assumption that meant that H.M. Millington was male, and I referred to he. And Ravi said, no, stop. Millington was a she. So I felt very, and so actually HM stands for Hillary Margaret. But she very sadly died in her late 20s. So, and I think this was sometime in the 60s or the 70s. I found the obituary of her.
I think maybe she was senior to me also.
Maybe so, yes.
Thank you.
okay, so any more questions?
Yeah, these Weierstrass P function that you get from period lattice.
Yes.
So if you want to get the lattice from the Weierstrass P function, probably one has to take the roots of the cubic, and the roots are E1, E2, E3, and then E1 equal to P inverse of omega 1 upon 2, and from that one gets the period lattice.
Yeah.
This is one possibility, I think, to get the period lattice from the this thing. Or is there any better way of getting the?
So I think, can I just rephrase what you have just said as to how you would do this? That if you were to, we have these image points of infinity E1, E2, and E3, and then I have the corresponding elliptic integral. If I evaluate that integral along a path between two of those points, then that's exactly corresponds to what I will end up with is, I think, half of the period. And so it's effectively evaluating path integrals, and but of course I have a choice of path because between those 2 points, because I could go on the other side of one of the other points, and that's exactly the monodromy that I talked about in the last slide. And so monodromy is all about choosing path integrals that would give me my lattice. I think that's the best way to think about that.
Okay. Yeah,
I think the rest of this semester is perhaps going to give you some tools to be able to do that, and not just for the Weierstrass function, but for other hypergeometric functions.
Okay. Yeah. Thank you very much. Nice talk.
Okay, so that's great. So is there any more questions? Okay, so I think John will share the slides with Devendra, and he will post them on the web page. And so if there are more questions, then people can ask in the next talk or during some discussions Okay, so thank you very much for your talk, John. So on behalf of the organizer, I thank you.
Well, thank you very much for the invitation. It's been a pleasure.
So with this, I think we will end this session of this year-long program. I thank both the speakers, Sasha and John, for their wonderful lectures. So we hope to see you soon.
Okay.
So Devendra, would you like to say anything before we leave?
No, we see them next week again, next Tuesday.
Okay, that's great. So bye-bye.
Same time. See you.
Bye. End poll.
What is it?